You are listening to The Vocal Technologist. Spoken tech for your ears.
Welcome back. If you blink this week, you probably missed, 5 major releases and a whole new architectural paradigm. The pace is just relentless.
It really is. But that's why we do this. We try to find the actual signal in all that activity.
Exactly. Our mission today is to take all these fascinating developments in DevOps and platform engineering and distill them into something you can actually use.
And as we went through everything, one clear theme just kept popping up: friction. Every single advancement is about reducing friction.
Friction in what sense?
Well, whether it's the agony of a slow incident response, the headache of manual config, or just raw network latency, engineers are finding really clever ways to just remove it.
Okay, I like that frame. And what we've been looking at points to 2 huge movements, right? First, AI is moving from being like a cute coding assistant to a core operational teammate.
It's taking over the real grunt work.
And second, the infrastructure race has just pushed scaling to limits that. I mean, they honestly feel like science fiction compared to a year ago.
So let's start with that first theme. There's a development that should make every on-call engineer just breathe a huge sigh of relief. The AWS DevOps agent.
Yes. The public preview.
We've had bots that open tickets for a while, but this feels different. It seems like an AI agent designed to automate the incident response itself. What makes this such a leap forward?
I think the breakthrough isn't just the AI doing one task. It's the ability to eliminate what we call swivel chair operations.
Right, that horrible moment where you have 10 tabs open and you're trying to piece things together.
Exactly. An alert comes in from CloudWatch, you check the logs in Datadog, then you're digging through recent commits on GitHub to find a correlation. That's 5 minutes of painful context switching.
And 5 minutes can be the difference between a minor blip and
a major outage, for sure. What's fascinating here is its comprehensive automatic correlation. The agent connects directly to all those tools, CloudWatch, Datadog, GitHub, you name it, and correlates that data instantly.
So it's not just flagging an issue, it's presenting a narrative.
Precisely. It identifies potential root causes and even suggests specific preventative measures, all in one report. It crushes resolution times.
That correlation sounds incredibly powerful. But where's the potential catch? Does linking all those tools create a new kind of single point of failure for the SRE team?
That's a fair question, about managing the complexity of the agent. But the goal is to centralize the data and the response, not the whole infrastructure. And it goes beyond just identification.
How so?
You can configure it to automatically triage incidents, grab diagnostics, and then plug right into ServiceNow or PagerDuty. For anyone suffering from alert fatigue, it's genuinely transformative.
And people can try this now.
Yep. It's in US East and Virginia, and the preview is no charge, though there's a limit on the agent task hours per month.
Okay, so shifting gears a bit from responding to incidents to maybe preventing them. AWS is also rolling out AI assistance for infrastructure setup itself. They're calling them Managed Control Plane, or MCP servers.
Right.
For listeners who hasn't run into that term, what exactly is an MCP server, and how does it stop those infamous config disasters?
A managed control plane in this context is basically a dedicated, fully managed environment for your container infrastructure, whether that's EKS or ECS. These new MCP servers give the AI tools real-time cluster context without a developer needing to set up anything locally.
So the AI is always working off the most current, secure source of truth instead of a developer's 6-hour-old local environment.
Precisely. And the infrastructure handles the tedious parts for you: automatic updates, IAM security, CloudTrail auditing. It takes a massive cognitive load off the developer.
And they have one specifically for infrastructure as code, the IAC MCP server. Why is that so significant?
Because writing reliable IAC is surprisingly hard. Tools like CloudFormation or CEK can be incredibly finicky about syntax and dependencies,
I think we all know.
This IAC MCP server is designed to help an AI assistant search documentation, validate your template logic, and troubleshoot deployment failures. It removes a huge layer of friction, less time debugging YAML.
And speaking of making AI smarter, we saw some crucial updates to Amazon Bedrock Agent Core. They mentioned policies and evaluations, but the phrase that jumped out at me was episodic memory.
This is where it gets really interesting. Episodic memory means the agent can learn from past interactions. It's not just looking up an answer and then forgetting it happened.
It's building experience.
Yes, we're moving toward agents that get empirically better over time based on their successes and, just as importantly, their failures.
So that changes the game. If an AI agent remembers, hey, last time I saw a latency spike here, adjusting this specific setting fixed it, but changing that other one caused a cascading failure, that memory becomes invaluable operational knowledge.
It creates a feedback loop that humans really struggle to maintain under pressure. The updates are about control and learning, sure, but episodic memory is the engine for real self-improvement. It really boosts the level of trust you can have in it during a crisis.
Okay, that's a serious amount of intelligence being injected into ops. Now, let's pivot hard to our second major theme. Pure breathtaking scale. The infrastructure race is just peaking, and Google Cloud announced an experimental 130,000 node GKE cluster. 130,000. That number just sounds made up.
It's not just impressive, it's a statement about the absolute limits of distributed systems. I mean, this cluster sustained 1,000 pod creations a second and managed over 1 million objects. That's a huge engineering feat.
What actually made that possible? What was the secret sauce on the control plane?
It seems to be two main things. First, some major control plane optimizations to reduce bottlenecks in the Kubernetes API server. Second, integrating queue for advanced scheduling.
Ooh, queue, for those who don't know it.
It's essentially a job queuing system for Kubernetes. It's vital for those massive AI workloads because it makes sure training jobs can be queued up and scheduled without just overwhelming the entire cluster. It's proof that GKE can handle these huge, bursty AI demands.
So, if Google is pushing the absolute limits of raw capacity, how is AWS meeting the demand for consistency and predictable performance? Because consistency can be way harder than just scale.
That's the key distinction, isn't it? AWS is focusing on guaranteed stability with the Amazon EKS Provisioned Control Plane. For a huge SaaS platform or a big AI company, predictable performance is totally non-negotiable.
So how did that provision plane deliver that guarantee?
It works by pre-allocating dedicated capacity in defined tiers. So you're moving away from the standard shared resource model. By reserving that capacity, AWS guarantees your scaling limits, ensuring your critical workloads perform predictably no matter what else is happening in the region. It's all about the SLA.
And to manage all that complexity, they introduced Amazon EKS capabilities. Sounds like an abstraction layer for common tools.
It is, and it's meant to address that complexity tax that comes with EKS. It offers fully managed solutions like Argo CD or AWS controllers for Kubernetes. The main benefit is that these tools run in service-owned accounts.
So you get the power of the tools, but AWS handles the maintenance.
Exactly. They handle the scaling, patching, and updating of the control mechanisms, which saves the platform team a huge burden.
Okay, we've covered these hyperscale success stories. Before we move on, let's inject a little necessary cynicism. We saw a great insight recently about platform architecture.
Yes. The quote we saw was, "Resume-driven architecture leads platform teams to amass tools instead of solving business needs."
And we've all seen it.
Oh, absolutely. It's that cynical reality where teams adopt the shiniest new tool for marketability, not utility. And it usually ends in a complex, costly, and delayed migration that doesn't actually help the business.
Which makes our next point, a real success story, even more impressive. LinkedIn just completed a massive architectural shift.
This is a perfect example of doing it right. They replaced their decade-old Zookeeper-based system, which was just crumbling under their scale, with a new architecture powered by Kafka and XDS.
And XDS is the Discovery Service API used by tools like Envoy.
That's the one. The key takeaway is the performance gain. They achieved near real-time data propagation, a P50 of less than a second, and a P99 under 5 seconds. It supports hundreds of thousands of app instances and solves that Zookeeper scalability problem.
That's a major modernization effort that was clearly focused on a business need. And speaking of foundational architecture, we have to talk about the unreasonable effectiveness of SQLite.
Oh, this one is fantastic.
The numbers are wild.
Yeah.
100,000 transactions per second, over 1 billion rows. How is a single file database even in the same league as a big network database?
It's not magic, it's just physics. You're eliminating the slowest part of any database equation, network. SQLite operates in the same process as your application.
So its limitation is its advantage.
In this context, yes. By using a single radar model, it enables incredibly efficient batching and concurrency control, all without the overhead of TCP/IP and network serialization. Its supposed limitations become massive performance advantages over something like Postgres for certain workloads.
And when is this a terrible idea? Where should you absolutely not use SQLite?
Well, you shouldn't use it when you need true transactional guarantees across multiple independent writers, or if you need centralized data access from different hosts. But for high throughput, read-heavy local caches or serverless functions, it can be an absolute beast.
Sometimes the simple tool wins, but often you just need the fundamental tools to get better. Let's shift to the developer experience, starting with some major language updates.
For sure. We saw Django 6.0 drop, and it's a huge feature release. They're adding things like template partials, built-in background tasks, and improved security via a built-in content security policy, or CSP.
And making CSP built-in is a big win, right? It pushes developers toward better security defaults.
It's security by default, which is the gold standard. Meanwhile, PHP 8.5.0 introduced a new URI extension, and most notably the pipe operator, which will make functional chaining much cleaner.
And then there is the elephant in the developer room, TypeScript. The update on TypeScript 7, Project Corsa, this might be the most significant structural change we've seen this week.
It is huge. This is a total performance commitment. Project Corsa is the fast native rewrite of the compiler and language service. For years, TypeScript was constrained by running on Node.js. By rewriting it natively, they're shedding all that overhead.
And we're already seeing the results.
We are. They're reporting major performance gains and that the new toolchain is becoming stable. They've also confirmed that TypeScript 6.0 will be the final major JavaScript-based release.
Wow.
It's been a massive week for platform engineering, and here on The Vocal Technologist, we love seeing this kind of future-proofing. For every developer dealing with slow builds and large monorepos, this is a lifesaver.
Speaking of performance, let's pivot to security visibility. The battle against malicious traffic needs better tools, and Cloudflare improved its wave logging in a really clever way.
This is a great efficiency improvement. Previously, if a rule triggered, the wave might log the entire request body. Huge logs, high costs, hard to debug. Now the new payload logging captures only the specific fields that triggered the rule.
So that sounds tactical, but what's the strategic benefit there?
The material we saw indicates it reduces log size by 67%. Strategically, it means a security engineer can see instantly why a rule fired, which speeds up fine-tuning and reduces false positives. Less noise means faster resolution.
It's that theme again, reducing friction. And on the open source side, we saw updates to Tempesta FW.
Right. Tempesta FW is built on a high-performance Linux foundation for fighting bots. The upcoming 0.9 release has a full tool set for detecting and blocking L7 DDoS attacks.
L7 being the application layer, which is always harder to block.
Exactly. Their Web Shield component uses ClickHouse for analytics and their own proprietary Tempesta fingerprints, or TF, to classify clients. This isn't just IP-based. TF uses a binary hash at the TLS and HTTP layers to create a deep fingerprint.
Which makes it much harder for bots to hide.
Much harder. It allows for more effective machine learning-driven blocking, even if they keep changing IP addresses.
We've covered scale and speed. Let's wrap up with resilience and the bottom line. We have to start with a pretty sobering statistic about small and mid-sized businesses.
Yeah, the landscape for SMBs has just completely changed. This year alone, they faced a 273 times increase in cyber attacks. Detected threats surged to over 13.3 million.
So enterprise-level threats are hitting businesses without enterprise-level resources.
That's the terrifying reality. It just underscores how important simple default security measures are, which is why something like managed container image signing, which is newly supported by Amazon ECR, is so essential.
It makes it easy to verify a trusted source.
Incredibly easy. It gives these resource-constrained businesses a layer of security resilience that's becoming an absolute necessity.
Well, finally, let's talk money. We need speed and stability, but also financial flexibility. How is AWS helping with database spend?
The big news there is the AWS database savings plans. We're all used to these for compute, but this is new for databases. You commit to a consistent hourly usage, and you can get up to 35% savings on services like Aurora, RDS, and DynamoDB.
That's more flexible than reserved instances, right?
Much more flexible. It applies across different incidents, families, regions, even database engines. And interestingly, the highest savings are seen in serverless deployments, which really encourages modernizing your architecture.
That makes serverless even more attractive. And EC2 introduced a clever way to reuse dormant capacity.
That would be the interruptible capacity reservations. It lets organizations reuse their unused reserved capacity for fault-tolerant workloads, like batch processing or testing.
But the owners can get it back anytime.
Instantly. The original owners can reclaim that capacity whenever they need it. So it turns idle capacity into a low-cost asset and maximizes utilization without compromising availability. It's a really smart way to tackle cloud waste.
What a week. So we saw AI shift into automating core operations, incident response, config validation, and now agents even have episodic memory. Infrastructure scaling limits were just shattered by that 130,000 node Kubernetes cluster. And foundational tools like TypeScript are getting serious native rewrites to keep up.
My final thought for you to explore really centers on that contrast. On one hand, we see Kubernetes scaling to this monumental size. But at the same time, we saw a tool called Kamera get released, which lets developers simulate and model check Kubernetes controller logic on a laptop. So what does that trend extreme scale on one hand and desktop verification on the other tell us about the future stability and complexity of these systems? What stands out to you there?
Are we designing systems so complex that they require precise simulation before they even leave the desktop, even as they're running on a cosmic scale in production? That's a fascinating question about complexity and control. Thank you for joining us. We hope this helps you navigate how these shifts will impact your workflow next week. We'll talk to you next time.
Spoken Tech for your ears.